Good morning, everybody. Welcome to today's class. In today's class, we'll continue with our lesson on the transformer. In the previous class, we looked into what is a transformer, what is the necessity of the transformer, why transformer part of a power system, and also we understood what is the principle of operation, how the transformer works, and also we looked into different types of a transformer that are available based on various factors, based on number of turns, right, step down, step up, based on the type of a construction is used, based on the type of the cooling mechanism that is used. On various factors, we saw there are different types of transformer, the classification of the transformer we saw. Then also we understood how the power gets transferred from the primary side to the secondary side. There is no direct electrical connection between the primary winding and the secondary winding, but they are connected magnetically. So on the primary side, we will have the supply, and on the secondary side we will have the load. That is how the power get transferred from primary to the secondary, and the transformer has ability to transform the voltage or the current from one level to the other level. In today's class, we understand what is the EMF equation of a transformer, how it is derived, so that we can quantify, means how much voltage is induced in the EMF, right? That we can find out using the derivation of the EMF equation. This circuit diagram is a representation of the transformer. This winding on the one side, left hand side, this is the representative of a primary winding, and the two lines are representative of the magnetic core, and this winding is a representative of the secondary winding. And for the primary winding we have two terminals, and for the secondary winding we have the two terminals. The supply is connected to the primary winding. In this case, V1 is the primary voltage or the primary terminal voltage, and N1 is the number of turns on the primary winding, and E1 is the primary induced EMF, or you can say primary EMF E1. And when we connect the load, the current that is drawn in the primary winding is I1. So I1 is the primary current, N1 is the number of turns on the primary winding, V1 is the primary terminal voltage, and E1 is the primary induced EMF or the primary EMF. And on the secondary winding side, we have N2 is the number of turns on the secondary winding, and E2 is the secondary induced EMF or secondary EMF, and V2 is the terminal voltage on the secondary winding or secondary voltage. So load is connected here. When load is connected, it will start drawing the current. I2 is the secondary current or the current on the secondary side. Okay, so these are the notations that we are going to use for our derivation. So you will specify and you will say what are these notations. V1 is primary terminal voltage or the primary voltage. V2 is secondary voltage or the secondary terminal voltage. N1 primary turns, N2 secondary turns, and E1 primary EMF, E2 secondary EMF, and F is what? Frequency of the supply voltage or frequency of the primary voltage. Now we will considering that the primary side is applied with the V1 is applied on the primary side. When we apply the primary voltage on the, what will happen? It will result in a current, right? We already understood the principle of operation. When we apply the voltage on the primary side, it will result in a primary current, that is I1. and once that current I1 starts flowing, it will create a magnetic field. Okay, and that magnetic field through the core, it will get linked with the secondary winding. And what kind of a voltage we have applied? We have applied the alternating voltage. It will result in alternating primary voltage, will result in alternating primary current, and that alternating primary current will result in a alternating magnetic flux. And the magnetic flux is given by the instantaneous equation for the magnetic flux. Phi is equal to phi m sin omega t. Means what? The magnetic flux also, when current is zero, magnetic flux is zero. When current is maximum, magnetic flux is also maximum. When current is maximum in the negative direction, the flux is maximum in the opposite direction. So the magnetic flux also follows the a sinusoidal path. So that is represented by phi is equal to phi m sin omega t. And what is the principle of operation? Principle of operation is whenever the flux linked with a magnetic, whenever a flux linked with a conductor or a coil changes, and EMF is induced. That is how the our transformer operates. And this is nothing but the Faraday's the first law. And according to the Faraday's second law, what does the Faraday's second law states? The first law states that how EMF is induced. If you answer the question how EMF is induced, the answer is Faraday's first law. Whenever flux linked with a coil or a conductor changes, an EMF is induced in that particular coil or a conductor. The second question is how much EMF is induced. So you want to quantify, right? How much EMF is induced. That how much EMF with the Faraday's second law. What is the Faraday's second law? Faraday's second law states that the magnitude of the EMF induced is directly proportional to the rate of change of the flux linkage. So in terms of the equation, E1 is proportional to d phi by dt, or E1 is equal to N1 d phi by dt, and here by dt, and we can replace phi is equal to phi m sin omega t. Therefore, we get n1 into d by dt of phi m sin omega t, and is it is as omega is equal to 2 pi f. Phi m is what? Phi m is the peak or the maximum value of the flux, and one is the number of turns on the primary side. Therefore, even is a constant, and into sine omega t minus 90. So it indicates the the phase of the applied voltage. Okay, this represents the phase of the applied voltage. So this is nothing but the instantaneous equation for the induced EMF is given as E1 some constant into sine omega t minus 90 degree. Now this represents this, whatever the value we are going to get, Okay. I thought I got disconnected. Where was I? What portion was I was? Did the derivation complete? Anyone?
So you were at the end.
Huh?
So towards the end of the derivation.
Okay. Rest I will take a little quickly. So what we got is this equation. That is E1 is equal to N1 phi m 2 pi f sine of omega t minus 90. So this is a representation of similar to E is equal to Em sine omega t. That means what? This is the maximum value of the primary EMF. Therefore, I can represent this as E1 max. Means what? The maximum value attained by the primary EMF E1, that can be given as 2 pi f n1 into phi m. Now, as we know that we are going to represent the voltage as the RMS value, and what we have is the peak value of the primary EMF. We can always represent peak value in terms of RMS value, because we know the relation between the RMS value and the peak value. What is the relation? RMS value of alternating quantity is equal to 0.707 peak value, or that is also equal to peak value divided by root 2. Therefore, the RMS value of the primary EMF, that is capital E1, is equal to E1 max divided by root 2. E1 max is this one. Therefore, we can write the, the RMS value capital E1 is equal to 2 pi f n1 phi m divided by root 2. That will come as E1 is equal to n1 phi m. So this is the equation for the primary EMF. So important equation and important derivation from the exam perspective. You have to remember this equation, and based on this equation we can solve the problems. In this equation, what is capital E1? It is the primary EMF or the primary induced EMF, is equal to 4.44. F is the supply frequency, N1 number of turns on the primary side, phi m is the peak value of the flux. Then on the similar basis, we can do the derivation for the secondary EMF, that is capital E2. And if we do the derivation on the secondary side, we get the equation similar to this. E2 is equal to 4.44 F N2 into phi m. If you notice this equation and this equation, what changes is only the number of turns. If if the E2 is the equation, then we have to use N2. If E1, that is for the primary EMF, we have to use the primary turns, that is N1. Now, sometimes they in the exam they will not give the peak value of the flux. Instead, what they will give the peak value of the or the maximum value of the flux density, and also they will give the cross sectional area of the core using the maximum value of the flux density and the area of the core. We can calculate phi m. Phi m is equal to Bm into A. Next, voltage transformation ratio. This is a one important factor how we can easily understand whether it is um, a step up or the step down transformer based on this value of the voltage transformation ratio. And how do we define the voltage transformation ratio? Voltage transformation ratio is nothing but the ratio of the secondary EMF to the primary EMF. And already we know the equation for the primary and the secondary EMF. We can substitute here. E2 is 4.44 F N2 phi m. E1 is 4.44 F N1 phi m. All these values 4.44 F and phi m will get cancelled. What remains is N2 by N1. Therefore, E2 by E1 is equal to N2 by N1. And if you remember in the earlier when we started discussing about the transformer, we did this derivation where we proved E2 by E1 is equal to N2 by N1. And if it is ideal transformer, Okay, remember ideal transformer means what? There are no losses. If we consider a transformer to be a ideal transformer, then E2 is equal to V2. What is the meaning of that is, if we have a ideal transformer, that is there are no losses, then this E1, whatever we derived, E1 is equal to V1 and also E2 is equal to V2. But in reality, the E1 and V1 will be not equal in the practical transformers. But if you consider ideal transformer, then this voltage and this voltage are exactly same. If that is the case, then voltage transformation ratio can be written as, for ideal transformer, E1 is equal to V1 and E2 is equal to V2. Then what we can write, E2 by E1 is equal to N2 by N1 by is equal to V2 by V1, and current will go in the reverse direction. I1 by I2 is nothing but the voltage transformation ratio, where K is the transformation ratio and it is defined as the ratio of secondary EMF to the primary EMF. Efficiency of the transformer, we will solve a few problems and then we will return back to the efficiency of a transformer. As I told you, efficiency of the transformer is very high. It is in the range of 90 to 95% or even more than that, because transformer doesn't have any kind of a moving parts, so its efficiency is relatively high. But there are certain losses that occur in the transformer, and we will see what kind of a losses that transformer will have. And also the efficiency of the transformer keeps on changing according to the load. We will see why it keeps on changing according to the load. Then we will see a condition where the efficiency of the transformer is maximum, and we are going to derive that condition where the efficiency of the transformer is high. First we will see some problems based on the transformer. Okay, whenever the transformer rating is given, it will be given like this: 2000 oblique 200 volt. What is the meaning of this is, the first voltage that is specified is always the primary voltage, and the second voltage that is specified is the secondary voltage. So for this particular transformer, the primary voltage is 2000 volts and secondary voltage is 200 volt. And when they specify this is nothing but the RMS value of the primary terminal voltage and the RMS value of the secondary terminal voltage. That means what? This is V1, capital V1, and this is capital V2, comma 20 kVA. So transformers are always rated in volt amperes. They are never rated as watts. Okay, because depending upon what the load is, what the load will have certain load factor, according to the that the consumption will change. But transformer are always represented as volt amperes. V2 into I2 will be equal to 20 kVA, right? Okay. That is the transformer has 60 turns, 66 turns in the secondary. That is N2 is equal to 66. Calculate primary turns. Okay. Calculate primary turns. Number two, primary and secondary full load currents, neglect the losses. Now, what is this value? This is V1, this is V2, and full load kVA is 20,000 volt amperes. Then 66 turns on the secondary, that is N2. What we have to find first is N1. So because neglect the losses, or even if they don't specify like that, you can assume it as a ideal transformer. In case of a ideal transformer, we know that E2 by E1 is equal to V2 by V1 is equal to N2 by N1. So just now we saw that. So V1 is equal to N2 by N1. We know V1, V2 and N2. Only unknown is N1. We can easily calculate the N1. So what they have done here is they have directly created the calculated the voltage transformation ratio, that is V. V2 is what? Secondary voltage. Secondary voltage is 200. Primary is 2000. We get it as 1 by 10. 1 by 10. Therefore, N2 by N1 is equal to K, that is 1 by 10. Therefore, N1 is equal to N2 into 10. We did the classification. Guys, am I audible?
Yes, sir.
Okay. There were some beeps were there. I was just wondering it got disconnected. Right. We saw the classification. The first classification is based on the turns, right? If we have, if N2 is greater than N1, then we will have a step up transformer. Means what? The voltage will increase on the secondary. If number of turns on the secondary are less than the primary, we will have a step down voltage. So here it is a clearly a step down voltage. On the primary side we have 200 volt, and on the secondary side we have sorry, on the primary I have 2000 volt, and on the secondary I have 200 volt. Means voltage is stepping down from higher voltage to lower voltage. Similarly, the number of turns will also decrease. When they given the 66 turns on the secondary, means that the number of turns on the primary side are higher. That is with the just the idea of the classification. That is how you can verify your answer. So more voltage means more number of turns, less voltage means less number of turns. That is why we get 660 turns on the primary and 66 turns on the secondary side. Once we calculate the primary turns, next what we have to do is primary and secondary full load currents. First, I will tell you what is the meaning of the full load. The transformer rating is 20 kVA. The maximum load that you can put on this transformer is 20 kVA. Okay, you cannot exceed 20 kVA. So this full load means what? 20,000 volt amperes. You need not load the transformer fully. Let us say you just loaded the transformer to 10 kVA. Means what? You have loaded that particular transformer to half of its load, load. And how this load increases, it depends on what kind of a load you are connected to the secondary. If secondary load draws 20 kVA, then it is a full load. If the connected load draws only 10 kVA, then it is a half loaded transformer. Now what they are asking is primary and secondary full load current. Means this transformer is loaded to 20 kVA. What is the meaning of that? If I multiply the VA, volt into current, both on the primary side as well as the secondary side, V2 into I2 will be equal to 20,000. So where V2 is the secondary RMS value of the secondary voltage, I2 is the RMS value of the secondary current. This will be also equal to V1 into I1, where V1 is the primary RMS value of the primary voltage, I1 is the RMS value of the primary current. Therefore, we can write V1 into I1 is equal to V2 into I2 is equal to 20,000 volt amperes. So using this, if I take V1 I1 is equal to 20,000, V1 is already given. I can calculate I1. So I1 I get it as 20 into 20,000 divided by V1. V1 is 2,000. So 20,000 divided by 2000, we get it as 10 amperes. Similarly, I calculate the full load current on the secondary side, that is V2 I2 is equal to 20,000, or I2 is equal to 20,000 divided by V2, which is 200. We get it as 100 amperes. Now you can see the inverse relation, right? What is the meaning of the inverse relation? On the primary side, voltage is high, 2000, and the current is low. On the secondary side, the voltage is low, that is 200, but the current is high. That is how we get that equation, right? We get this V1 I1 is equal to V2 I2, or you can rewrite it as V2 by V1 is equal to I1 by I2. That is how we, in that voltage transformation ratio earlier, uh, here this is how this is reverse. If you compare here, V1 I1 is equal to V2 into I2. That's why you remember, whenever you are using this voltage transformation ratio, this is E2 by E1, N2 by N1, V2 by V1. But when it comes to the current, it just reverses, I1 by I2. Okay, so we have found out so whatever is asked in the particular problem. Next problem: an ideal 25 kVA transformer has 500 turns on the primary winding and 40 turns on the secondary winding. The primary is connected to 3000 volt 50 hertz supply. Calculate primary and secondary currents at full load. Secondary EMF, that is E2, the maximum core flux, that is phi m. All those things we have to calculate. They have given it's the ideal transformer, 25,000 VA, that is the volt ampere rating of the transformer. It has 500 turns on the primary winding. Means what? This is N1 is equal to 500 and 40 turns on the secondary. N2 is equal to 40. So here you can make out it is a step down. On the primary we have more turns, secondary less turns. And primary is connected to 3000 volt 50 hertz supply. 3000 volt is nothing but the primary voltage, that is V1. F is 50 hertz. We have to calculate primary and secondary full load currents. Okay, similar to earlier case, the transformer will be loaded to 25,000, and we are going to say V1 I1 is equal to V2 I2 is equal to 25,000, and we will find I1 I2. First one is finding the K, voltage transformation ratio, N2 by N1. Both are known. That is 40 by 500, 4 by 50. Now, I1, how do we get this I1? The volt amperes, whatever volt amperes at full load, V1 I1 is equal to the 25,000, or I1 is equal to volt ampere divided by V1, that is 25,000 divided by 3000. We get it the 8.33 amperes as the full load primary current. Once we know the full load current, either you can use V2 I2 is equal to 25,000, or you can use the voltage transformation ratio. K is equal to I1 by I2, or I2 is equal to I1 by K. You can use any method, you will get the same answer. So 8.33 into 50 by 4, we get it as 104.2 amperes. Now you can observe, on the primary side, the voltage is high and current is low. On the secondary side, if you calculate, the voltage will be lower, the current is higher. Now, we know E2 by E1 is equal to K, or E2 is equal to K into E1. Because it is an ideal transformer, V1 is equal to E1, that is V1 is equal to E1 is equal to 3000 volt. Therefore, K into E1, 4 by 50 into 3000, we get it as 240 volt. So secondary has 40 turns, that's why the voltage is also less. E2 is equal to 240 volt. Now, what we have to find? Maximum core flux, that is phi m. And what is the equation? You have to just to remember in which all equation phi m is there. Phi m is there in the EMF equation for the primary voltage, that is capital E1 is equal to 4.44 F N1 phi m, and second equation is phi m is equal to Bm into A. Bm is not given, A is not given. But in this particular equation, we know most of the values. E1 is given, okay, because V1 is equal to E1 is equal to 3000. F is given, number of turns on the primary is given, only unknown is phi m. So if you substitute all the value, then you can calculate the phi m. So phi m comes as 27 into 10 raised to minus 3 Weber or 27 milliweber. Next problem. So this is based on the EMF equation. A single phase 2200 volt slash 250 volt means this is V1, this is V2. F is equal to 50 hertz. Transformer has net core area of 36 centimeter square and a maximum flux density of 6 Weber per meter square. Now they have given the cross sectional area of the core, that is 36 centimeter square. You have to make sure that it is represented in the meter. Okay, and what is 36 centimeter square? It would be is equal to 36 into 10 raised to minus 4 meter square. And bm is given 6 Weber per meter square. Calculate the number of turns on the primary and secondary. Now we know the equation for EMF equation. E1 is equal to 4.44 Fn1 into phi m. Why we have to use this equation? Because only N1 is the unknown, rest are known. Which are the other equations I can use? I can use V2 by V1 is equal to E2 by E1 is equal to N2 by N1. But in those ratios, we don't know, those values are not given. So we cannot use that particular formula. Here E1 is given, E1 is not given, V1 is given, but it is an ideal transformer. We can assume it as an ideal transformer. V1 is equal to E1 is equal to 2200. So E1 is 200, 2200. Frequency F is 50 hertz, that is given. N1 is unknown and phi m is not given, but Bm and A are given. Therefore, phi m is equal to Bm into A. What is Bm? 6 Weber per meter square into area represented in meter square, that is 36 into 10 raised to minus 4. We get it as 0.0216 Weber as the flux. Now all the values are known in this equation except for the N1. Therefore, N1 is equal to E1 by 4.44 F phi m. You substitute all the values, you get it as 459 turns. So on the primary side, how many turns are there? 459 turns. To find out the number of turns on the secondary, we can use two methods. Either you can use this formula, E2 by 4.44 F phi m. E2 is 250 and rest of the values are same. Frequency is 50 hertz. Phi m we just calculated here. So all those things will remain and you will find N2. What is the other way? Since we already calculated N1, we can use the voltage transformation ratio, right? E2 by E1 is equal to N2 by N1, and that is how N2 is equal to E2 by E1 into N1. That way also we can calculate. And if you these are the terms, if you get fractional numbers here, just round it to the whole number, because number of turns will be always in a whole number. Next, a single phase 50 hertz transformer has a square core, 20 meters centimeter side. The permissible maximum flux density in the core is 1 Weber per meter square. They have given the Bm, maximum flux density. Bm is given, and they did not give the area. They have given one side of the core is 20 centimeter side, 20 centimeter. So we have to calculate the area. Calculate the number of turns per limb on the high and low voltages. High and low voltage sides of a 3000 divided by 220 volt. So high voltage side is primary, low voltage side is secondary. We have to find the N2, N1 and N2 values. To allow for insulation of stampings, assume the net area in the length to be 0.9 into gross iron length. Now, one thing is there, the stacking is done in between. They use the any kind of a insulation material which will hold together. So effective length will get reduced. What they are saying is one side is it is 20 centimeter, there is no issue. On the other side, because of the insulation of the stampings, the length is 90% of the gross length. Means what is the gross iron length? 20 centimeter, but it is only 10% is gone in that insulation. We have only 90%. So 0.9 into 20, that is 18 centimeter. Now what is the area? 20 centimeter into 18 centimeter, that is the true cross sectional area, and that should be represented in meter square. Therefore net iron length 0.9 into 20 centimeter, that is 18 centimeter. Net cross sectional area A is equal to 18 into 20, we get it as 36 centimeter square, which is nothing but if you multiply it by 10 raised to minus 4, you get it as a in terms of uh, meter square. Therefore area is equal to, we get it as 0.036 meter square, and flux you can calculate, phi m is equal to bm into a. Bm is given as 1 Weber per meter square into 0.036. So this is the flux, 0.036 Weber. Now you know the flux, then you know the value of the E1, you know the frequency, we can calculate the number of turns, N1. Therefore N1 is equal to E1 divided by 4.445 Fm. Assume this as an ideal transformer, therefore V1, this given V1 is equal to E1 is equal to 3000 divided by all this value, we get 375 is the number of turns on the primary side. N2 we can calculate it in two ways, as I told before, either using the E2 equation, E2 is equal to 4.44 F into 5M, or we can use the voltage transformation ratio, that is E2 by E1 is equal to N2 by N1. N1 is already calculated, E1 and E2 are known. You can find out what is the value of N2. So it will come as 27 turns. Okay. The next problems are based on the efficiency. We will look into the efficiency in the next class. So, as a simple idea, what is the efficiency is how much output we get for the given input. If I say 90% efficiency means for the given input, means 100% input, I get 90% output. So that is the efficiency, and efficiency is nothing but the ratio of output power to the input power, and it can be represented as a percentage, or it can be represented as a fractional value. If it is represented as a percentage, let us say 90%, means that particular transformer is 90% efficient. Means if you give like input of 100, it will give you output of 90. That is how the efficiency, and that is in terms of a percentage, 90%. The same thing can be represented as a fractional value. 90% is nothing but 0.9. We'll see that in the next class.